Okay, welcome to the second of the videos about uncertainty and how to take measurements so that they're the best that you can get. This one we're going to move on to a slightly different area, and this one's actually bringing in this idea of percentage uncertainty. So I'm going to bring in some terminology that's probably new to you, but it's big in engineering and within other areas as well. So we're going to look at this idea of how far off the readings are and how bad that is. So last time we had the idea of the stop clock, give or take half a second to start and stop. Is that bad? Well, not if you're timing for 3 hours. 3 hours, give or take half a second, is much smaller a problem than if you had 3 seconds, give or take half a second. Okay, so we're trying to bring in the idea so you know how bad your results are roughly. So we'll start off with an example here. Again, it's back to the measurements of the resolution of the measuring instruments. So here we've got two balances. This is to the nearest gram, so plus or minus 1 gram is the uncertainty. This one is the nearest hundredth of a gram, plus or minus 0.01 grams. And we're going to use it to basically check some chocolate. So what we've got here is 2 packets of Twixes, and according to this, it's 160 grams. So for the 4 packs inside, that's obviously 40 grams in each. So if it's less than 40 grams, it's actually illegal. They have to sell it at that mass. But are they actually 40 grams? Well, what we've got here, if I just take one of the packets, for example, and stick it on, we see even on the first one isn't. So I'd already zeroed it, so that's definitely 44 grams. This is calibrated as well, so we know that this is accurate, this scale. 42, 42, and 40. So they're all at least, but if we go to a more precise scale, well, again, 42 isn't 42. Yeah, these were both the same on that scale. They're both different when we go on to a more precise scale. Okay, so we're measuring a more uncertainty, smaller uncertainty. So, is that a problem? Well, we could just, of course, stick the whole thing on. Like we said last time, take multiple readings and divide by 4. But this wouldn't give us an accurate result, because if we think about it, we've got plastic, yeah, and that's almost 1.5 grams on its own, plus we've got the plastic on each one as well. So what we'll find is all the readings will be a bit off. There will be a piece of systematic error, which is we know we're including the plastic as well, but we can still use it to find the variation. We can still use it to find percentage uncertainty, roughly. So what we're going to do here is I'm just going to grab a whiteboard, and we're going to write down what the values are so we can use them. And first one then, we'll put it on. Again, you can do the maths of this at home, and we'll do the precise reading. So that's 41.74. You can see it jump around a little bit, but if you notice me blowing on it, affects it a lot as well. So you've got to be really, really clever with your readings, and you've got to be really careful when you take measurements as well. That's why if you have a chemical balance, what you have the proper one is they're enclosed within a glass shield so that you don't get any variation. So 41.75 when it settles. Let's split open the other packet while that's waiting for that to settle. 43.85. Before I leant over it. Drop one, that won't help, but it's still in the packet, so don't worry. 40.76. 40.76. 42.70. 43.99. When I'm not blowing on it. 41.10, 'Didn't like that. Let's reset that one. And must have made it land on the bottom as I slid it off. And again, set it at 0, 39.84, so that's actually under the limit. Okay, so if that was an individual packet, an individual Twix, then that would actually be under the limit allowed. But because it's part of a multi-pack, as long as that whole multi-pack is bigger than that. So some chocolates are bigger than others. So, what is the actual mass of a multi-pack or a 4-pack of Twixes? Well, obviously we can take these, and the best thing, and what most people would do, is to find the arithmetic mean. Add them up, divide by 8. Okay, and that will give us a fairly good value. But it's not the greatest value. Because if we had something that was way off, so for example, there's 2 up here that are 43, way bigger than the others really, that's almost 44. That's, if it's again rounded up, that's 44. Those 2 are much, much bigger than the others. And so that will actually change your average. Those 2 will affect the average quite a lot. There are ways around it. There's other ways of finding the average. So rather than doing the mean, you can do a geometric mean. It's called an RMS value, a root mean square, which you will see when we get it to upper sixth. Or you could do the median, which generally gives you a much better value for the average reading. However, what we could do, and this is what we tend to do in physics, is we could plot these as a graph. So if I plotted these as a graph, I could do that, and I could find the average value. So there's my 8 bars, for example. I plot them, and then I put in a line across to find the best. And you can see how much they scatter above and below from the readings. But again, where do you fit that? Because they're supposed to be the same. So actually, where do you decide to put your line across? So it's far, far better to get yourself a diagonal graph. So what we could do is actually take first reading, then for 2 bars, then for 3 bars, and we'll just keep piling them up, taking the reading each time. And as we do that, I'll get higher and higher. And then it's much easier to put a line of best fit because you will actually see where the fit is. You'll see where the trend is. So from this, you can see when we added on this bar here, it's quite scattered from the line. It's far off the line, which means that its mass is much, much bigger. That's an uncertainty. Okay, in this case, the ones we measured, then there's probably going to be 2 that are quite far off the lines, but the rest of them you get a good line of best fit. And if you divide the mass by the number of bars, in other words, if you find the gradient, you're always going to get an accurate value. Okay, so that will give you a true value. So when that stuff came at GCSE, when you started talking about uncertainty a little bit and started talking about the true value, well, the best value you can get is always going to be the gradient of a line of best fit. Okay, so this is something that's built in, and a lot of safety equipment has this idea built in. One example is in electronics. So what I've got here is a multimeter, and the multimeter, I don't know if you can see the value too well, let's tip it up a little bit more. The value gives us our resistance. So what I have is 10 resistors out of a packet, okay, and they're all out of this highly stable carbon film resistor, 1/2 watt, so it's not designed for a lot of current because it would get too hot, and the resistors are 4.3 kilo ohms. We can tell that by looking at the colours. So there is a colour coding on all resistors because it's too small often to write the values. So what we have here is yellow, then a red, then an orange. Okay, and the colours run through with black is 0, brown, red, orange, yellow, green, blue, violet, grey, white. So we can get all the numbers through with that. I forgot purple, sorry. And so with using that kind of rainbow effect, we can work out that those say 4, 3 with 3 zeros after it. So we can get that, 2 values zeros after it. So we can get that as 4.3 kilo ohms or 4,300 ohms. There's a 4th band on though, which is the tolerance. We'll come back to that in a second. This one is gold, and most resistors tend to be gold nowadays. And that's because there is this uncertainty. So if we just measure them, you can see straight away that we have got different values. So we've got 4.33. That one is 4.30, which is what it should be. 4.30 again, so that's 2 in a row. That's the value it should be. 4.27. 4.30. So of those 5, 3 of them are actually at the value it should be, but there's a little bit of variation again. So again, they'll take multiple readings, they'll do this, but there's got to be an error, because actually what this is just a length of carbon, okay, of certain width, a certain length, and they try and chop them all the same to give you the same value. You're never going to get them perfectly the same. So that's why you get this variation. Now, this gold band on here means that all acceptable ones are within 5%. Gold represents 5%. If it was silver, it'd be 10%. So what we can do is we can take those values there, and in this Blue-Peter tradition, I've already measured them. And so what we can do is we can find out if all of these resistors are within that band. Okay, just a quick glance, you could probably guess they are, because you can see that. But any that were outside that 5% will be thrown away. NASA, in one of their early space missions, their rocket not blew up, it actually burnt up, it set on fire on takeoff. It hadn't left the ground, and the reason, they hadn't even fired the rockets, the reason is because the heating up of the electricity flowing through the wires changes resistance. Resistance changes with temperature, and they'd tried to get all their resistors exactly on, and they'd forgotten about or hadn't catered for enough heating due to all the resistance. So there's always going to be a bit of give or take, and you always use a rule of thumb. So these values have every value between 4.27 and 4.33. So actually those form the 2 limits of our readings, and your average is going to be somewhere in the middle. Now if you take the average of those 2, that's exactly 4.30, which is what it should be. But what we end up with is a little bit of uncertainty within that. So it's built into all our readings. We should have the same, but what we've got is this range on the repeated readings. Now this technique only works for repeated readings, but we know that if that is our average value, then our reading should be plus or minus within a certain thing. And so what we take is the whole range, and the range from there to there is 0.06, and that's plus and minus from that full range. So actually, sorry, 6. So what we'll do is we'll half that, and that will give us, in this case, 0.03. That is our uncertainty. Okay, so our uncertainty is plus or minus 0.03. So that tells us how good the readings are, but we want to see if it falls within the range. And so there's a couple of key things with all readings, not just electricity, and I've summed them up on the board here. So the first thing is, that uncertainty is comparison by the range. But if I wanted to find out different resistors and they were 2 ohm resistors, then 5% of 2 ohms is completely different from 5% of 4,300 ohms. So we need to scale them to the same. So we tend to put it as percentage, because most people are happy with that and can use that really well. So what we need to do is, from that, we can then see if the measurements are too big. And this comes up in all news events. You have to justify how good your readings are. A few years ago, Italian scientists from the CERN, over the border from CERN, they were measuring the time it took for particles to be fired through a specially made tunnel through to Italy, and they found that things were breaking the speed of light. Now, the speed of light cannot be broken. If it is found to be broken, we'd have to change all our laws of physics. And so what they did was they released all their data, and they found that actually measurement errors, not errors, but the measurement uncertainty in all their instruments meant that actually it went lower, or some of the results could be lower than the speed of light, and so in the end they realised that it wasn't. But it was only when they released it everyone saw that. So you're going to have a tolerance, and you're going to say, is that acceptable? Are my readings within 20%? If so, that's good. Some things you might, like the resistors, want them to be within a smaller precision, okay, a smaller uncertainty, so 5% would be better. So how do you do it? Well, you take your true value, your best value, okay, that it should be, so that's from your data, and then you take that give or take uncertainty. So in this case, I would take 0.03. My average, if I add them all up, actually comes out very, very close. So 0.03 over 4.31, okay, sorry, 29, correction. And so if I multiply that by 100, I'll get it as percent. And that tells me, even just looking at that, you can see that 3 over 429, that's really small. Okay, so that's less than 1%. So all of these resistors are within 1%. They're all within the tolerance that they should be. They're all within their decided maximum offset rating, which is 5%. They're all good. Okay, so that is how percentage uncertainty works. It's how you take half that range to actually work it out. And again, key points. You'll use that in biology, you'll use that in chemistry, you'll use that in physics. If you're repeating readings, half of the range between the biggest and lowest reading is taken to be your uncertainty, even if the average isn't in the middle. Okay. Mean, not so good. So using that as an average is, if you can avoid it, go without. For physics, we definitely do a lot with graphs. So plot it on your graphs. You'll see, as I say, the scatter. You'll see how far off those results are. And the crucial bit is, if you've got a nice diagonal line, a nice linear graph, then your line of best fit is that true value. That gradient is the thing to use in all your calculations, because it will be way better than individual readings. It will always give you a much, much better answer. Okay, so in a nutshell, that's percentage uncertainty. We're going to use it a lot and all the time. Just keep thinking, how far off is that? Is that good or is that bad? Because that gives you an idea of how well you're doing your experiment, and more importantly, how trustworthy, how reliable is your data.